The Axiom of Choice. Welcome to this video. This video is to give a short, non-technical introduction to the historical development of the Axiom of Choice. I'll deliberately not be going into deep technical aspects of the axiom in this video because firstly, I'm not an expert in the technical aspects of the axiom, and secondly, I really do want to focus more on some of the historical and philosophical aspects. However, from time to time, I may need to touch briefly on some of these technical aspects. This video is based on information drawn from several sources, but the main source is the book titled Zermelo's Axiom of Choice, Its Origins, Development and Influence by Gregory H. Moore. This is an excellent book which gives a very thorough treatment of the history of the Axiom of Choice. It can get somewhat technical from time to time, but the book is very readable if you're interested in that kind of thing, and will give a good understanding of the history of the axiom both leading up to its explicit formulation at the start of the 20th century and the consequences of the axiom after its introduction. Moore's book runs for some several hundred pages and is very detailed, so naturally in a relatively short video such as this one, many details have had to be omitted and there will inevitably be some loose ends. I've tried my best to pick out what I think are some of the main points, and I've tried to go into as much detail as I feel is appropriate without getting too involved. I regret, however, that I have had to omit a considerable amount of detail. So, what is the Axiom of Choice? Well, there are various formulations of the Axiom of Choice, and I'll present a few of the formulations that have been given from time to time. I'll firstly take the formulation of the axiom given in Moore's book, which goes as follows. Given any family T of non-empty sets, there is a function f which assigns to each member A of T an element fa of A. The Axiom of Choice, as given in the book An Introduction to Analysis by Brown and Piercy, is let C be a collection of non-empty sets, and let U denote the union of the collection C. Then there exists a mapping Z of C into U, called a selection function or choice function on C, such that ZE is an element of E for each set E in C. Clearly these statements of the Axiom of Choice depend on sufficient definitions of set, mapping, union and so forth, but we'll assume that these are sufficiently well-defined concepts or primitive concepts for the above statements to make sense. In Max Black's The Nature of Mathematics we read, given any class of mutually exclusive classes of which none is null, there is at least one class which has exactly one term in common with each of the given classes. Black goes on to say that this formulation of the Axiom of Choice is often called the multiplicative axiom, since it has been used in defining the product of an infinite number of cardinal numbers. There are all kinds of symbolic formulations that different authors might give, which depend to some degree on what the context is in which the axiom is intended to be used, and also at what point in time the formulation is given. Some older statements of the axiom may seem too imprecise to a modern reader. However, in the book Set Theory and the Continuum Problem by Smulyan and Fitting, we see an intuitive interpretation of the axiom. The authors speak of a somewhat controversial, though highly important principle known as the Axiom of Choice, which in one form roughly says that, given any non-empty collection of non-empty sets, it's possible to simultaneously choose exactly one member from each of the sets. There are also many propositions which can be shown to be equivalent to the Axiom of Choice, or which are stronger than, in other words, imply the Axiom of Choice, but are not implied by the axiom, or conversely, which are weaker than the axiom, that is, implied by but do not imply the axiom. And details of many of these can be seen in the appendices to Moore's book. I can't give an exhaustive list of all of the propositions that are equivalent to the Axiom of Choice, because there are just so many of them that it's not even worth trying. But since I have a particular fondness for Whitehead and Russell's Principia Mathematica, I'd just like to quote an equivalent from that work which is known as the multiplicative axiom. Throughout the history of the development of the Axiom of Choice, there has often been considerable confusion about propositions which are in fact equivalent to the axiom. We see in Moore on page 39 that although many propositions are logically equivalent to the Axiom of Choice, they've not always been psychologically equivalent. At various periods and to various mathematicians, these propositions have possessed differing degrees of self-evidence. Sometimes one of them seemed true and another false. And an amusing quote attributed to American mathematician Jerry Boner, whose work I have to confess I'm not familiar with, is, the Axiom of Choice is obviously true, the well-ordering principle obviously false, and who can tell about Zorn's lemma? The Axiom of Choice, the well-ordering principle, and Zorn's lemma are all logically equivalent propositions. So I'll just make a few comments on why exactly I got interested in the axiom of choice in the first place. For me personally, the axiom of choice is particularly special because this axiom was one of the things that really led me into further studies in the history and philosophy of mathematics. Once I started to realise that this axiom was not as simple as maybe initially thought, and indeed has been a very controversial introduction into mathematics. The axiom of choice is something that I remember encountering a couple of times during my undergraduate mathematics studies. In particular, I remember it being used in the proof that certain sets of real numbers are not Lebesgue measurable, and I also remember an equivalent version of it being used, Zorn's lemma, in the proof that every vector space has a basis, not just finite dimensional vector spaces, but any vector space, whether finite or infinite dimensional. And I don't suggest that the use of the axiom of choice is erroneous in contemporary mathematics. I think that there is good reason for mathematicians to accept and freely use the axiom of choice, since many interesting results can be derived from it, and ultimately it is up to mathematicians to decide for themselves what they do and do not want to accept in their own field. And although I don't recall the exact sequence of events now, it was the various references to the axiom of choice in the book An Introduction to Analysis by Brown and Pearcey that originally really made me start to realise that there was more to this axiom than I'd initially realised or been led to believe, whether deliberately or accidentally. And moreover, it was my further investigations into this axiom that eventually led me into the philosophy of mathematics, and to a certain extent to more general philosophy. I eventually came across Moore's book, and I was fascinated by the history and controversy of this axiom that hitherto I'd had no real idea about. So let's have a brief look at some of the initial history of the axiom from the mid to late 19th century and to the early 20th century. Towards the end of the 19th century, it was becoming clear that some mathematicians, and amongst them notably George Cantor, were using a technique in their proofs that was difficult to precisely formulate. But some mathematicians were getting increasingly unsettled by whatever it was that was going on. It was being implicitly assumed that infinite arbitrary choices could be made. Evidently, many of the mathematicians using this technique, infinite arbitrary selections or choices, were completely oblivious to this, in inverted commas, new principle. And it was other mathematicians, such as Peano, reading these proofs who started to notice something different going on, but at the time were unable to properly identify and formulate what seemed to be happening. In Moore we read, Cantor created a body of important theorems in which the assumption of infinite arbitrary choices was unavoidable, and through which its implicit use was absorbed by many other mathematicians. Hence, when later researchers examined the underlying presuppositions more closely than Cantor had done, they found a special axiom of existential character was at work. Moore identifies 4 periods of development within mathematics leading up to the appearance of what would eventually become the axiom of choice. These periods are only intended to give a rough idea of the progress of mathematics over a period of approximately 2 millennia, but listing these periods goes some way to explaining what kind of change seems to have been stealthily taking place in mathematics during the late 19th century. These are given in section 1.2 of Moore's book as Stage 1, choosing an unspecified element from a single set or the arbitrary choice of an element from each of finitely many sets, examples of which can be found in Euclid. Stage 2, an infinite number of choices by stating a rule. Stage 3, an infinite number of choices but leaving the rule unstated, possibly initiated by Cauchy. And Stage 4, an infinite sequence of arbitrary choices for which no rule was possible, as seen in Cantor. And of course, it's this final stage that most concerns us here. So let's look at an example of how the assumption of infinite arbitrary choices entered into the proofs of certain results. Here's an example from Cantor 1895. Every transfinite aggregate T has parts with the cardinal number Aleph naught. This theorem is stated in Moore as 1.1.4 that every infinite set A has a denumerable subset. And this theorem may seem fairly obvious, but the point is that there is a principle being used, and which is in fact unavoidably being used, to prove this theorem. This principle is a form of the axiom of choice. Bertrand Russell, in his Principles of Mathematics in section 118, makes the claim, it's very easy to show that every infinite class contains classes whose number is alpha naught. where alpha naught denotes the least infinite number. Russell proceeds to make an implicit use of the assumption of infinite arbitrary selections in much the same way that Cantor did. And Cantor's proof, although simple and quite convincing, requires the axiom of choice, or at least a form of it known as the denumerable axiom of choice. In More, on page 10, it's stated that the denumerable axiom is required and that there is in fact a model of ZF in which a certain infinite set of real numbers lacks a denumerable subset. Neither Cantor nor Russell give any indication of how to define such a rule which chooses the elements from the classes. This is significant because it turns out that it isn't possible to give such a rule. Thus we have an example of a situation that corresponds to stage 4 in the previously mentioned list. Much work has been done to establish which theorems make an unavoidable use of the axiom of choice, or some other related or equivalent principle in their proofs. Even when the underlying principle of infinite arbitrary choices was identified, though not necessarily fully formulated, many mathematicians continue to use it without realizing. Even some who did not support the notion of infinite arbitrary choices were inadvertently using the principle. The history of the axiom of choice is intimately bound up with the history of attempts to prove, amongst other things, the well-ordering problem, or principle, or theorem, depending on the view taken, that any class can be well-ordered. And secondly, the trichotomy of cardinals, that is, that for any two cardinal numbers, m and n, then m is less than n, or m equals n, or m is greater than n. The former, Cantor originally proposed as a self-evident logical law, but Cantor's opinions on both the well-ordering problem and trichotomy of cardinals varied throughout his career, sometimes viewing one or both or neither as self-evident. For example, we see in More a quote from an article by Cantor. The concept of well-ordered set turns out to be essential to the entire theory of point sets. It's always possible to bring any well-defined set into the form of a well-ordered set. Since this law of thought appears to me to be fundamental, rich in consequences and particularly marvellous for its general validity, I shall refer to it in a later article. This indicates that at the time of writing, Cantor believed the well-ordering principle to be a self-evident law of thought, and in section 2 of Cantor's 1895 work, we see some comments on the trichotomy of cardinals. The theorem that, with any two cardinal numbers a and b, one of those three relations, equality, less than, or greater than, must necessarily be realized, is by no means self-evident and can hardly be proved at this stage. And also in Russell's Principles of Mathematics, again in section 118, it is not at present known whether, of two different infinite numbers, one must be greater and the other less. The trichotomy of cardinals seems at first glance to be a perfectly reasonable proposition, but we read in Stephen Corner's The Philosophy of Mathematics, if a and b are finite numbers, the following three relations may hold between them. A equals b, a is greater than b, or a is less than b. If a and b are transfinite, it is prima facie not inconceivable that they are not comparable with each other. In order to establish the same kind of comparability between transfinite as hold between finite cardinal numbers, set theorists had to assume that every class can be put into a certain standard order, even if no effective method is known for achieving this. The assumption is that every class can be well ordered. It has been subsequently shown that the well-ordering problem and trichotomy of cardinals are both equivalent to the axiom of choice, and therefore equivalent to each other. And it was in particular the well-ordering problem which eventually attracted the attention of Ernst Zermelo. Prior to this, Cantor had often claimed to prove the well-ordering problem true and at other times false. However, in 1904, Zermelo presented his own proof of the well-ordering problem and provided an explicit and precise formulation of the principle that would become known as the axiom of choice. I don't want to cover in any real detail the full contents of Zermelo's proof. I want to concentrate on the reactions to the proof, and more specifically, on Zermelo's introduction of the axiom of choice after identifying and making explicit the principle which had for so long remained unnoticed. Indeed, in Corner we read that the axiom of choice is implicitly assumed in a great deal of analysis and set theory only became clear to mathematicians after Zermelo discovered it to have been a tacit assumption in the proof that every class can be well ordered, and that in consequence the cardinal numbers of any two finite or infinite classes are comparable. And in More, Zermelo's demonstration of the well-ordering theorem began with an arbitrary non-empty set M for which a well-ordering was desired. Letting S be the set of all non-empty subsets M' of M, he made the first explicit statement of the principle later called the Axiom of Choice. To each subset M primed, one associates any element M1 primed, which occurs in M primed itself, and which may be named the distinguished element of M primed. We also see elsewhere in More on page 6, Zermelo regarded the axiom of choice as codifying an assumption that numerous mathematicians had already made implicitly. And on the same page, before that date, 1904, a mathematician who made such choices seldom recognised that he had done anything unusual or questionable. And on page 149, also in More, we read, the axiom's self-evidence, he, Zermelo, believed, was corroborated by the fact that, independently of each other, many mathematicians had used it implicitly. As grounds for its necessity, he cited its applications in set theory and analysis. Both Zermelo's proof of the well-ordering problem and his axiom were not at all universally accepted. There were many supporters and many dissenters. Some accepted both the proof and the axiom, others accepted one but not the other, and of course there were those who rejected both. So let's have a look at why there was such difference of opinion to, in particular, this new axiom. It's maybe quite difficult to imagine that an axiom could indeed be controversial, yet the controversies surrounding the axiom of choice lasted for decades and caused huge divisions within the mathematical community between those who accepted the axiom and those who rejected it. The axiom was rejected by many who thought that its use was taking mathematics in an undesirable direction by introducing concepts and techniques which, according to some, had no place in mathematics. We may need to take note of something at this point. Mathematicians around the end of the 19th and early 20th century were often, but not always, very influenced by philosophical considerations. Certainly much more so than mathematicians typically are today, and it's these philosophical considerations that often led to some mathematicians rejecting the axiom. But why? The axiom, when interpreted in certain ways, suggests that an infinite number of selections can be made in a finite time, and even where it's not possible to state a rule about how the selections are to be made. Arbitrary selection. There are also some philosophical issues concerning whether the selections are made independently of one another, independent selection, or whether a selection is made which depends on the selections that have already been made, dependent selection. In the former case, the selections can simply be thought of as occurring simultaneously. Of course, we still have an infinite number of selections being made, but the time aspect is eliminated. In the latter case, time seems to play a more fundamental role, because the selections necessarily have to be sequential. There were many mathematicians who considered the notion of infinite, or at least uncountably infinite, totalities to be wholly rejected as nonsense. And so to these mathematicians, the axiom of choice in its most general form was equally nonsensical, since the axiom applied to classes of classes, or sets of sets, of arbitrary cardinality. Other objections to the axiom were given at various times during the first half of the 20th century, which were of a more mathematical nature. Indeed, acceptance of the axiom of choice leads to several counterintuitive and sometimes undesirable results. For example, the discovery of a bounded, non-measurable set proved to be one of the more controversial consequences of the axiom. Some of these counterintuitive results are often called paradoxes rather than theorems. Because these paradoxical results often make a necessary use of the axiom of choice, that is, they can't be derived without the use of either the axiom of choice or some related proposition, then it's been easy for those mathematicians against the axiom of choice to point towards these results as evidence that the axiom of choice is not acceptable, by claiming that the results are not merely counterintuitive but contradictory. Those objecting to the axiom thought that they were onto something when Felix Hausdorff presented his seemingly paradoxical result, which evidently showed, through use of the axiom, that one half of a sphere was congruent to one third of the same sphere. These paradoxes are not necessarily true paradoxes, or at least are not considered paradoxical in modern mathematics, because mathematicians have found satisfactory explanations. So unfortunately for those critics of the axiom trying to use Hausdorff's paradox as an argument against the axiom, this result does not necessarily imply that the axiom is wrong, and that it produces contradictory results. One explanation of Hausdorff's paradox is that it simply shows that Lebesgue's measure problem has no solution, a result which may be undesirable for some, but not at all contradictory. And once mathematicians decided that they were prepared to accept this idea, then this explanation prevailed, and thus the axiom retained its acceptability in the eyes of many. And just for clarity about the essential role the axiom of choice plays in proving that unmeasurable sets exist, we also see in Moore, it is now known that the existence of a non-measurable set cannot be deduced in ZF. As well as the objections to the axiom, there were many mathematicians who gave justifications in favour of the use of the axiom within mathematics. Some mathematicians thought that philosophical considerations were being taken too seriously, and that the axiom should not be rejected on philosophical grounds. Others, including, as we've already seen, Zermelo himself, noted that infinite arbitrary choices had been used by so many mathematicians without even realising it, that it suggested that the axiom was therefore self-evident. Others noted the utility of the axiom in mathematics. Application of the axiom had produced many interesting and rich results that naturally appealed to a wide range of mathematicians, and to deny the axiom and bar its use in mathematics would impoverish mathematics. Therefore, the axiom could be accepted on pragmatic grounds. It turns out that there are many important results in mathematics that make unavoidable use of the axiom, and so to ban use of the axiom would mean that these results would be invalid. For example, the following result from real analysis is one such result. A real function f is continuous at a point p if and only if f is sequentially continuous at p. The Polish mathematician and logician Sierpiński, we're told in Moore's book, provided evidence in support of the axiom. Sierpiński claimed that many particular cases of the axiom had been verified without using it. Mathematicians had deduced numerous consequences from the axiom, none of which had led to a contradiction, and the axiom was essential to the proofs of many important theorems in set theory and analysis. Moreover, as time went on, the axiom was being used in more and more results within mathematics. It was becoming increasingly difficult for those mathematicians wanting to avoid use of the axiom to do so because they may use a result of another author in one of their own proofs, which somewhere had a dependence on the axiom. Thus, they were inadvertently using the very thing that they were so critical of. Some mathematicians found the axiom to be so natural and unremarkable, and completely accepted the axiom and its use, such as Hausdorff, that they wouldn't even bother to mention its use in the proof of a result, and so, unless the proof was given a careful reading, it could easily be overlooked that the axiom had even been used. Other mathematicians agreed that the axiom was acceptable, but agreed that it seemed to have a special status, and only used the axiom when it was absolutely necessary, and would often note its use explicitly in their proofs. Some critics of the axiom noted its non-constructive nature. Indeed, the axiom was seen to have serious ontological implications, that is, with regards to what it meant to say that a mathematical object existed. The axiom of choice seems to simply assert the existence of a function, a choice function or selector function, with certain properties without actually constructing the function. Moreover, results derived using the axiom are often, if not always, of a non-constructive nature. That is, it's simply shown indirectly that there is an object with certain properties, but no such object is or can be exhibited. This may seem fairly uncontroversial to modern mathematics, where existence theorems are fairly common, but at one time to show that a mathematical object existed usually required a construction rather than mere assertion of its existence. What constituted a construction was not necessarily clear, but nevertheless a construction, whatever that meant, was usually required. And we see in Moore, the axiom epitomizes a fundamental transformation that took place in the late 19th and early 20th centuries. The use of the actual infinite throughout mathematics, a byproduct of set theory, made it evident that existence and construction were vastly different mathematical concepts. Jacques Hadamard, a supporter of the axiom, says in a letter addressed to Émile Borel, and as quoted in Max Black, writes, "What is certain is that M. Zermelo gives no method of effectively carrying out the operation of which he speaks, i.e., of making the infinitely many choices, and it remains doubtful whether anybody could finally indicate such a method. But the question of effectively giving a function is different from that of proving its existence." Hadamard further says in the second letter to Borel, "Can the existence of a mathematical entity be proved without defining it? I reply in the affirmative. The resistance that some mathematicians had towards accepting the axiom of choice may be due to simply being too comfortable with the status quo, which was potentially threatened by the introduction of the axiom of choice into mathematics. We see in Moore on page 290, later mathematicians who had not been involved in the controversy were increasingly likely to apply the axiom with no qualms of conscience. and arguably this mirrors many behaviours that we can clearly see from one generation to the next, such as typically greater acceptance of, say, new technology amongst younger generations who tend to be on the whole somewhat less set in their ways and less dependent on maintaining the status quo. Whether the axiom of choice is true or false is of course not a mathematical problem but a philosophical problem. A mathematician is concerned with the consequences of various axioms, including the axiom of choice, but not necessarily with whether an axiom or collection of axioms is true or false, whatever it may mean to say that something is true or false. Admittedly, the controversies that surrounded the axiom during the first half of the 20th century have largely disappeared, and I can't imagine that there are many mathematicians, particularly those engaged in research in contemporary mathematics, who would seriously consider rejecting the axiom except to maybe explore some of the consequences of its denial. Its use is ubiquitous in contemporary mathematics. In A Course of Mathematical Logic by Russian mathematician Yuri Manin, writing in the 1970s, we see, over the past 50 years, it has become customary for every working mathematician to accept this axiom, the axiom of choice, and the heated controversies about it at the beginning of the century are now all but forgotten. In contemporary mathematics, the axiom of choice is used extensively in a wide variety of contexts: analysis, algebra, topology, logic, set theory, and so on. The axiom may often be used without even being mentioned, and its use may, therefore, be adopted fairly uncritically by the vast majority of mathematicians. In the book An Introduction to the Theory of Groups by Rotman, we see Zorn's lemma is equivalent to a much more intuitive statement, the axiom of choice, and goes on to say of Zorn's lemma and the axiom of choice that we regard both of these statements as axioms of mathematics, and we will not be ashamed to use either of them when convenient. Thus the axiom of choice and of course its equivalents have been completely absorbed into contemporary mathematics, and are freely used to prove many interesting theorems, and I expect that this will continue to be the case for the foreseeable future. So for those who want to know more about the history of the axiom of choice, then I definitely recommend reading Moore's book on the subject, which covers things in much more detail than I've been able to do in this short video. But that does bring us to the end of this video. If you have any questions about anything in this video, or if you have any suggestions for future videos, then please let me know. But thank you for watching, don't forget to subscribe to my channel, and I'll see you in the next video.